Hi all, welcome to Theoretically Podcasting. I have with me today my buddy Justin Kulp. How are you doing, Justin?
I am swell.
So Justin is currently finishing his PhD at the Perimeter Institute and shall soon join the Simon Center as a postdoc. Is that right?
Yes, the Simon Center for Geometry and Physics in Stony Brook.
Very good. And that brings us to the topic of our discussion, which is geometry and physics, the adult version. So tell us, Justin, what has been the focus of your research? Perhaps not lately, but but as it pertains to geometry and physics.
Yeah, sure. So, well, geometry maybe is too rich, but there's maybe something a little bit coarser, which is there's been a recent interest in sort of how sort of topological things in quantum field theory. So there's been sort of a renaissance in recent years studying studying what's meant by symmetry. So symmetries are very important in theoretical physics, and sort of the vanilla symmetries that you know in your everyday life, they can be global symmetries, they can be gauge symmetries, but usually they're what are called zero form symmetries, and we can go into detail about all the higher form symmetries and things like that. But roughly speaking, I mean, what are they? It means that, like, if you have zero form symmetries, I'll say first a word that I'll say that zero form symmetries are things that live on codimension one operators, like they have codimension one support in spacetime. We can go into the details if necessary. And so once you sort of understand this picture, a sort of natural generalization occurs, which is, can you consider higher form symmetries, which live on higher codimension manifolds, right? So
Sure.
That's one generalization of the notion of symmetry. And so one of the things that's important about symmetry operators is these manifolds that they live on correlation functions, which are the important quantities that you calculate in quantum field theory. They don't care, roughly speaking, about the topology of the surface it lives on. You can deform them in correlation functions, these surfaces, and or whatever they are. You can deform them however you'd like, and as long as you don't accidentally move them past an operator, the correlation functions will be invariant. And so, yeah, you can generalize this. You can say, oh, maybe I could study topological codimension 3 operators in a 7D theory or something like this. So that's one generalization. And then another generalization, which has been very interesting, that sort of actually came around the same time, is the notion of non-invertible symmetries. So roughly speaking, you know that if you have group-like symmetries, right, then what happens is, and you imagine that they're captured by these walls, right? So then you have like this wall implements a G symmetry, and then there's another wall that implements an H symmetry, and then you squish them together. Naturally, they must form some sort of GH symmetry, right? That makes total sense. I'm just telling you that, symmetries compose with group-like fusion rules. And then there's this natural question, okay, what if that's actually just not true? What if you could basically what if you basically just remove the sort of group-like condition? And, if you think about the conditions that make group associativity, having a product, having inverses, things like this, the natural thing that you want to remove is this notion of invertibility, right? So once you have both of these notions, these double generalization, you can have topological defects of any codimension and then topological defects that don't necessarily have to be invertible under fusion. You basically have what we have now in modern times. We basically identify all topological defects in a quantum field theory with some notion of symmetry, very roughly speaking. So that was long-winded, but that's the overview.
But let's like break that down. I mean, I wouldn't mind if we just spent our entire discussion today breaking that down, because I think it's worth understanding. So let's start with the very beginning about what you were describing. The form. Okay, so you said zero form symmetry, codimension one slices, correlation functions not caring about the geometry and small deformations of the slices. So let's like try and go through that somewhat slowly so that the rest of it kind of generalizes more quickly. So I suppose the first thing to note is that when you're talking, the degree you're referring to here is not the degree of, say, the gauge fields when we normally think of. So, I mean, if you're thinking about like what we're talking about here, we're really talking about the degree, the form degree of the gauge parameter, in a sense, the form
Uh,
degree of the symmetry generator when we say like zero form.
yes.
So
Yeah.
you basically are referring to the fact that, okay, so here we're already talking about the counterfactual. We're actually gauging the symmetry. We don't actually have to do that. But that's sort of the origin of the terminology. And I thought that that would be helpful just because this whole etymology has in the back of its mind the sort of basic pairing between forms and cycles, which I think is like, you know, the first thing to establish, right? I mean, why that's relevant here. And once we see why this basic pairing of forms and cycles works and how it works in conjunction with word identities, then the sort of first half of your explanation will become sort of very clear in the context of codimension one and zero forms, and then, you know, higher codimension and higher forms. So yeah, I mean, I shall leave you to sketch on the whiteboard, on the virtual whiteboard, if you would like.
Sure. So, I mean, what,
But yeah, I could also.
no, I can,
Or I mean, you want to
I
take the
can
lead?
sketch
Okay.
here, but, yeah, maybe you, okay.
Oh
So
yeah, okay.
what,
Maybe I can just proceed with some of the explanation, and then you take over afterwards. So
sure. Or I'll just nod.
yeah, or you can nod.
Okay.
Okay. Cool. So let's see. Basically, the let's start with the first statement, right? First statement is what is it? Zero form. Oh, didn't mean to yell. Symmetries. Codem 1.
Yes. So yeah, the statement would be zero form symmetries live on codimension one slices. So I was actually afraid you were going to make me try and explain Poincare duality or prove it or something live. So
Oh yeah, no, let's not prove anything. Let's just
oh,
make
perfect.
statements with with increasing levels of confidence.
I,
Okay.
I only
So
do lowbrow explanations. So yeah,
I mean,
I
it shouldn't be too hard. Let's figure this out. Okay. So
sure.
normally, what we mean, so we have the Noether theorem notion of symmetries, and
Yep.
we have currents associated with conserved quantities. They satisfy essentially continuity equations, right? These are sort of
Absolutely.
space-time continuity equations. So this is now a form on space-time. So J is in where is it? Omega. So how many? What do you want to call your dimension? D M.
It's a good letter.
Okay,
Yep.
right? Am I
And
right about this? It's not, right? It's not really that. It's going to be a one form because I want
yes,
star
J will be a
J
one
to
form.
be, yeah. So I want star J to
Yes.
be D minus one form, and then I want D star J to be top degree form.
Yes.
Okay.
And in particular, just, this is important to emphasize that this is, we're starting with something very normal and familiar to people, which is just a nice continuous symmetry group where you can have a notion of a conserved current, right? I mean, Noether's
Perfect.
theorem
Yes.
relies on, yeah.
Yeah, but I mean the reason why I still prefer it is that there's the second concept which you implicitly refer to, um, where you basically want to consider some correlation function. Right. So you basically wanted to
Absolutely.
consider. Okay, let's kind of break this down. There's word identities that we normally write in the following way. So if you write it in the local way, then we basically have so 1 up to n. There's the whatever the symmetry action on the local operator is, right, at the marked point. Um,
I need a delta function somewhere. Oh yeah, you got it. Wow, you're speedy.
I think it's like this. Yes.
It'll be delta x minus xi, yes, and then
Yeah, and
the
then there's the
correlation
rest.
function with, yes, with all the rest, and also
With
your
all the
delta should,
rest. So let's yeah, I mean the delta should be in, but I've pulled it out. But okay, that's right. So so
wonderful.
what I want is that I have phi x1 delta phi x I and phi xn. Okay, so the point is that this is just Noether's theorem worked into our definitions of the correlation functions. If you want, you could derive this from path integral or whatever. But ultimately, the statement that the only way for what we shall now or soon discover was secretly a codimension one object all along, the symmetry operator,
Sure,
to
yeah.
to affect things is to sort of cross the point at which a local operator is inserted, right? That's so
Yes,
the point is, and so that's sort of the topological nature of the operator relies on this identity, right? So at least in the
absolutely.
case where you have continuous symmetries and so on. So this is the word identity. So there's Noether's theorem, and then there's the word identity, which is sort of like the quantum upgrade of it.
Yes.
Okay.
I mean, another way to say it is if you imagine taking, I mean, this is, I just give successively more and more lowbrow explanations for things. But I mean, if you imagined taking the current, the current is J, and you know that a charge is the integral of star J over
Okay, let's do
some,
that.
okay,
Okay, let's do that. Let's do that.
do it.
I was going to get to that. So
Oh, sorry.
we should okay. So J belonged. So let's just go over this a little bit pedantically so that we can be fast in the rest.
Absolutely.
Star J therefore is in omega d minus one, and so if I wanted to integrate it, then I must choose some sigma which has dimension d minus one star j, right? And that's the available pairing between sigma and j, right? So I don't know, there's some abstract thing here. There's some abstract pairing which I'll just define like this. I might regret writing it like this later, but that's what I mean. And this thing defines the charge, right? This is the charge Q, charge Q associated to sigma.
Yes.
Okay, and now let's proceed with the rest of your discussion.
Yeah, so that defines this charge Q. And just as an aside, it's not super duper relevant, but this is the thing that you would exponentiate to turn into a group element.
Yes.
Later on. But what I was just going to say was, I mean, if you imagined having, so this might be a little hard for you to do in LaTeX Live, but if you imagined, space-time is just some empty white sheet of paper, and then it's smattered with you have x1 through xn, so it's smattered with n little dots like flying around, and then also jx, and then you imagined integrating over a ball. So you imagine integrating the word identity over a ball with volume, such that the boundary of the ball was that manifold sigma, right? So yeah, sorry, it's a dang.
So
You are
you're
lightning
saying that
fast.
there's gonna be like MD, right? So there's gonna be MD such that
absolutely equals the ball in question, or the
okay.
surface in question. And then well, if we take a look at the left hand side of this equation, I mean d star j integrated over this ball, this is basically just going to plop in the charge that we have
Q.
above.
Yes. So by Stokes' theorem, so
using
what exactly? So what Justin's saying is that here there's secretly the dx, and then here there's there may be some space to, so let's just take this to be flat for the time being, but whatever. Okay. And so we'll use Stokes' theorem here, right? It's this ddx, x1 to xn are essentially unintegrated. Xi here is also unintegrated. So what I can do is use Stokes' theorem to write this as D, which is sigma D minus 1, right?
Yep.
And here I have star j x. Rest of my correlation function comes along for the ride, right? But this is just defining Q
Yes.
yeah. So importantly, the integration, I see like the integration only really sees this thing here. So this is like the correlate. I can sort of bring the integral inside, as it were. Let me do that just to make things more clear for everyone listening.
Yep.
Right. And that is Q, right? So that's so at the level of the words we normally use, this is correlation function, local correlation function with the insertion of an actually non-local thing, right? This is integrated over codimension 1 surface. So it's like it knows about sigma, but importantly, there's the right-hand side. At the right-hand side, we can also do the integration. It's a sum of delta functions, right?
Yep.
And
so if
important
the
is
ball, if the ball wraps a particular delta function, then it's just going to capture the correlation function with that one field wiggled.
exactly. So it's going to have the sum. It's 1 to n of well, it's basically the sum of all of these.
I mean, as a specialization, just for simplicity's sake, let's just assume that the ball, the MD,
yeah,
was surrounding only one of the operators, and let's just say X1 for your own sanity. Then we're basically see that it's delta phi 1, and then also all the other phi n's. So perfect. You are so speedy.
Well, this is what happens when you're too lazy to get yourself an iPad and set all that up properly. So you have all the others which come in around. So so I don't have deltas. I just have phi x1. Oh, not x1. Phi x2.
Yep.
There's the ordering is gone now. But what are you gonna do?
It's all right. Let's assume.
Yeah.
Let's assume. Okay.
But phi, yeah, okay, go on. Yeah.
That's totally fine. Yeah. And then so what we've roughly seen is that because the symmetry operator has, roughly speaking, sort of engulfed that one point, it's basically done the symmetry action on just that one point. I mean, that's kind of the idea we're capturing. And just as an aside, I mean, I went and I grabbed very quickly this Q that we're defining is defined in terms of like, star J, and it looks a little bit mysterious. But when you take the manifold sigma to literally be a space-like slice of your quantum field theory, then I had to double check. I went and I grabbed Peskin. I mean, this is literally the same thing that Peskin defines in exercise 2 of the famous book. So Q is not mysterious.
Yeah, so just it'll be J0. So this is what D star J in components is. And then if I just took star, okay, so given that, and then I take sigma D minus 1 to be space, right?
Yes.
It's just that T equals constant. Then what I basically have is that star J integrated over sigma is the integral 3x of J naught, also known as rho.
Yeah.
The current density, the charge density. Okay.
Beautiful.
Right. So good. This is like, I guess, the basic example. But it
Yes.
also perhaps makes the point that, like, we're not always talking about a case where the sigma wraps around the charged operators. It could be some non-compact thing. It could be like it's the thing that goes out to infinity.
Absolutely.
But the important point here is indeed, like, now it puts your words before in context. The little wiggles are basically anything. So any little wiggle that doesn't make you cross one of these points, one of these marked points, is irrelevant in this formula, right? All it knows about is the sort of linking number between between this sigma and these points x1 to xn, and that's sort of what measures the charge ultimately on the right hand side. And so the important thing to note is that that's the origin of the topological nature of this operator, despite it being non-local. It's sort of subject to the rule that the void identity imposes on it. So now, I mean, the important point here was that there was sigma d minus 1 linked with the form here, which is, and this was still the so-called zero form symmetry. And we should probably explain the reason for that. The reason for that is that if we wanted to sort of gauge this symmetry, then in the Lagrangian, we would have a term. Well, it doesn't really even have to be the Lagrangian. Just in the generating function, you're going to have a term which looks like J. Well, right, plus stuff.
Yep.
And then the effect of the symmetry transformation would be, one way to see it is that we would have to compensate by making A transform as this. So now we're really in the U1 territory. And so this is a zero form, right? So alpha is in cool. So this is sort of the origin of the etymology. Alpha is a zero form D alpha, which has the same degree as J, or as well. D alpha has the same degree as J, correct? Is a one form, the star, which is D minus one form. So this is sort of why you have this. So then I guess let's jump to the generalization.
Yep.
Where we have so you have a codimension P surface, which is associated with the P minus one form symmetry.
Yes.
Right. I suppose the thing that people like doing is they want to talk about P form symmetry,
Yes.
so they make this P minus one or P plus one. Sorry.
P plus one. Yeah.
This is what the literature likes doing. Okay, cool.
Yeah. Well, it's helpful because yeah, you definitely chip me up. I've have such a habit for the slogan. The slogan that's burned in my brain is in this language. So
right.
okay,
Okay,
yeah,
good.
absolutely.
So yeah, I mean, let's just keep it consistent with most of the literature so that people don't get lost when they leave here and look through the great. So this is sort of like, and the rest of the story follows, right? That now this has a higher codimension, right? This is sort of by itself lower dimensional, and we can sort of see that, okay, charged objects here, well, what are they? They were point-like, right? Because you need something of codimension 1 to be able to trap a point, right? But like,
Yep.
if the codimension rises, you can miss, right? Like if it's just points we're talking about, you could totally miss.
Absolutely. Or well, yeah. Points can definitely miss each other. That's actually the best
Yeah,
example.
but I even mean like lines can miss points.
And yes.
And the fact that we're talking about topological things means that we gotta account for the fact that they can miss, right? Because you could make a small, like say you set things up so that the line hit the point, but now I just wiggled it a bit. Okay, now it's gonna miss, right? So
Yeah.
to have a sort of to necessarily have a linking number, you're gonna have to turn these. If you increase the codimension here, you're going to have to change the support of these from points to then perhaps lines to perhaps higher dimensional surfaces. So the charged objects go from being point-like, and they're themselves going to have some extent now. So this is sort of like the one obvious consequence of the generalization we have here.
Absolutely. And just to like, yeah, it's exactly what you said. I mean, and the best example is that points can miss each other even in 2 dimensions.
Yeah.
An example I really like is that you can't do knots, like you can't have knot theory basically in 4 dimensions with
Yeah.
four spatial dimensions. So, the fact that you can use string to tie things up heavily relies
Right.
on the fact that we have 3 spatial dimensions for the string to live in. So
yeah. So I encourage our viewers to try and tie their laces in 4 dimensions, just to have a hands-on check of this
absolutely.
claim. Cool. Okay, so now we have the sort of A's and the B's, and we can move on to the C's.
Okay.
Okay.
Right.
So let's there were 2 things you were discussing. So one is that you can have a generalization of these zero form symmetries to higher form symmetries, and as we see, a consequence is going to be that charged objects are no longer just point-like in space. They're going to have themselves some extent, so they're going to be extended objects in general.
Yep.
Okay, now what if what about all of this invertibility business? So let's let's go into that.
Yeah, sure. So I mean, where's the right place to start for that? I mean, in some sense, in some sense, for me, the way to describe it is again this a very lowbrow way, which is just what hopefully you've now been convinced of is the fact that if you have sort of these standard symmetries that you're familiar with, that they live on topological operators of some codimension. Maybe
Yes.
even and actually maybe sort of these higher form gauge fields are not so spooky to you if you've done higher form gauge series or something like that before. So these things shouldn't be very spooky. And roughly speaking, you're now convinced, or you now remember, that they are defined on these topological manifolds of some dimension. And so the question is now, what happens if you do one symmetry transformation and then the other? And the idea is that, typically we're used to them composing in a group-like way. And we can just relax that, right? So it's very possible that, you have some sort of topological defect in your theory that has the property that if you bring it close to itself, it turns into a sum of 2 other defects. So I don't know, am I allowed to talk about partition functions? I mean, you could imagine. Yeah. You could imagine.
But let's sort of also, I mean, just
Sure.
there's other facts that come with the higher form gauge theory story, and one of them, importantly, is that these higher form gauge fields, if you do no compactification of any kind, they're all abelian. They're just
yes, absolutely.
For the most part. I mean,
no, yeah. The proof of this is very simple. It's right. I mean, if you imagine, if we just go to a concrete example.
Yes.
Yeah. If you go to a concrete example of imagine three dimensions. So I'm drawing for you my space-time is like a box, and I have zero form symmetries, so they're represented by 2 walls. Then it's very obvious that if I do G and then hit it with H, it's different than if I had hit it with H and then hit it with G. Okay?
Yes.
Now, on the other hand, if I have little line operators, there couldn't possibly be a difference between hitting it with one and then hitting it with the other because their supports are topological, and I could just obviously move it around in one of the 3 directions and then smack it on. So That's the finger proof of
The finger proof.
yes.
Yeah, I mean, and it should be clear that okay, I mean, another thing to do, and this is just an exercise for the reader, is for the zero form case, right? Just to clarify the finger proof. I mean, we know how to get from word identities, right, involving currents, or in 2 dimensions current OPEs, to the commutator algebra of the charges. Right, so you have an actual charge operator as a commutator algebra, which represents the Lie algebra, which you can sort of confirm by just playing the same game, with the word identities. Introduce more than one charged operator, and see that when you do the integrations, then it's exactly as Justin said. You're going to have a difference between GH and HG. Now, the finger proof for the higher form symmetries becomes a lot more believable, right? Once you go to that exercise, you sort of understand that like this finger proof just becomes a lot more believable, that you can just jump around to the other side. But what can happen is that the symmetry just isn't forming a group at all, right? Like it's just not a group, and that's sort of the possibility that you're alluding to here.
Yes.
So, I mean, if it maybe helps, we can pull up some of the fine literature you pointed me to a few days ago,
Sure.
including some of your own work.
Okay. That's just
And
the literature then, not the fine literature.
it shall soon be known as the finest. Okay, well, here's a paper that. Okay, so but before we get any further, there's once the symmetries aren't really forming a group anymore, clearly there's another mathematical notion to take over from there, and it seems the one that's preferred at this point is that of a category. And so let's dive into the.
This looks like Tachikawa and Bhardwaj.
Yes, so this is Laksha, Bhardwaj, and Yuji Tachikawa's paper titled, I don't remember, but yeah.
On finite symmetries and their gauging in 2 dimensions. Yes.
Yes. So let's go to what they were. Yeah, okay. Symmetry categories, right? So that seems to be the thing it is that takes over from a group.
Yes, and mathematically they won't call them a symmetry category. They'll probably say some sort of word about, fusion category is probably the words they're looking for.
Yes. So here's what here's what they say mathematicians call them, as you say, is a unitary fusion category. Great. And so let's run over this with motivation behind each of these definitions, right? So Absolutely, the definitions are what they are. I think the important thing to understand is the motivation behind defining the notions. So to begin with, the objects. So here, okay, their focus is on 2D theories, and so in 2D theories for now codimension 1 is a line, and whatever. Okay, so even in this context, you can have a situation where the symmetry is not going to be captured by a group. So instead, we have the so-called unitary fusion category. Okay, the objects of this category are things you associate with lines. Okay,
yes,
let's hear it.
Yeah, no, I mean, yeah. Just to reiterate what you said, you should be able to basically, if somebody told you, you don't know what a unit. So this is like how physicists would do math, right? They say, you don't know what a unitary fusion category is, but you know that that's the thing that mathematicians say describe topological defects. Mm-hmm. Then you should basically be able to guess all of the definitions. So you should be able to prove all the definitions that you will need. Or at least argue them strongly. So the first thing first is when you're doing any category theory. And so concretely, they're focusing on 2D or 1 plus 1D for any condensed matter people out there. They're focusing on the 2D case, and they're going to be describing topological lines in 2D. But the formalism basically generalizes, right? I mean, it's a lot it's a lot more details, but the formalism basically generalizes. So they're going to be describing topological lines, and so this is sort of the codimension one object. So these are like zero form symmetries, and then they're non-invertible generalizations. So any category, the first thing up is you need to put some objects, because that's all categories have objects, and in this case, the objects are basically going to be identified with the lines themselves, so different species of lines. So, for example, if you were describing a theory with G global symmetry, then there should be a line for each element in the group.
Great.
Just as an aside here, it's also important to note that this formalism, until very, very recently, there's been some pretty great work that's come out by Christoph Weiss and others, but until very, very recently, and this formalism is basically largely restricted to theories with a finite number of symmetry operators. So basically symmetries which are particularly discrete.
Right.
So think discrete symmetry. So, U1 gauge theory would not be allowed, but Zn gauge theory would be allowed, right? Or something with S3 symmetry. Anyway.
Right. So and you're gonna have a finite number of objects essentially. If you have one per each group element, you just have you have a collection of them.
Or a finite number of simple objects.
Right. Okay. Good.
Yeah. Irreducible.
Good. Okay. We'll get to that too. Okay. Great. So for any line operator labeled by the object A, we have a partition function of T, the theory presumably, with the line inserted along an oriented path, which we denote as following. And yes, that makes sense. That's like if you thought about partition functions in general as if we're just talking about local operators, partition functions like a 0-point function, with nothing. Here, it's basically that you have a background defect. So you have a defect background and you're computing a partition function over that defect background, or you're computing something like a 1-point function, but it's not really 1 point. It's a one defect partition function. And that's sort of like the background over which the other local correlation functions are going to
if you're familiar with CFT literature, it'll be like a twisted partition function, basically.
Yes. Okay, good. We will get to that too.
Yeah.
Perfect. So now we have the morphisms, right? So morphisms. Let's get to what the morphisms are here. So yeah.
Yeah. So the morphism is basically telling you if you have one topological line, these are morphisms between topological lines. So any two categories have to have objects in morphisms. So, these are the two essential things that, you're going to need. And physically, what the morphisms are is they're basically describing how you can go from one topological line operator to another. So as they say, they're topological point operators, and they basically will, because, morphism is a functor, or not a functor, it's a morphism. It goes between two objects.
Yes.
So objects are lines. And so roughly speaking, this is a little dot, the topological point operator, which interpolates between the two lines.
Very cool. Okay.
Yep.
So somewhere we shall find a picture for that. Perhaps not here, but okay. Okay. So that's what the morphisms are here. They're the moving dots. Next, we have the existence of a trivial line, which is, okay, there's an object 1. I guess it's necessary to include in the definitions or in the, but
you better have
I don't know. Yeah, it's good to have that around, yeah.
Well, you need to be able to, if you look at a random blob of quantum field theory, and then, you need to be able to say it's not just packed with lines everywhere, right? You need to be able to say there's no line here, so there's an invisible line, roughly speaking.
Yes. Or that, when there's inverses, a inverse has to be 1. Okay, so then if you have, so there's an additive structure, which is that, I suppose it's to say that these are, if they're going to be operators on a Hilbert space, then presumably there's going to be some linearity associated with them, and you want that to be reflected in their behavior within correlation functions. And so that's what they're describing here, that the linear operator A directs on B, acting on the Hilbert space, is obtained by wrapping A sum B on a circle, which is then given by UA plus UB. So, okay, let's talk about the circle. Where's the circle?
So I mean, they're basically saying, in this case, I mean, the way that I imagine this here is if you imagined having, like, if you imagine quantizing the theory or something like that, and then they're basically saying that, well, and then I'm about to read to you the final sentence again. So
Sure, yeah,
so maybe
okay.
that's not a good.
Okay.
I was actually going to make a slightly different point though, quickly, which is that
Yeah, sure.
it's that this additive structure is not the squishing together of lines.
Nope.
Which is what
Right,
comes on
right.
which comes next.
Yes.
Which is in some sense the most important axiom comes next.
Right. So, well, I mean, okay, I don't think this matters that much as to why the circle is just probably the circle of space. If you think about the space-time as a cylinder. Okay. That's another convention to bear in mind. Okay, so let's get to the squishing, the tensor structure.
Yes.
So we have the object A tensor B in the category, which corresponds to considering two parallel running line operators as one line operator, which is just a squishing operation. Fingerproof is just you have two dimensions, so you can't really do the palms, you can only do the fingers. And the fingers are going to have to fall on top of each other. And when they fall on top of each other, you have the linear operator UA tensor B. And great, wow.
Defacing it.
I like how, yeah, I didn't know you could do that, but that's
well,
cool.
Okay, I guess I'm defacing everything, but yeah, I mean, it's basically just
Let's
that if
do
you
it.
take the two operators, they're topological. Quantum field theories, I mean, the most important piece of any quantum field theory is the notion of operator product expansion, and it applies even to lines. So I squish the red and the blue line together, and then it's basically just the same as saying, let's see, do I have purple? I don't have purple. It's saying that you can replace them if they come sufficiently close together in parallel. You can replace the parts that are sufficiently close together with a third line, which I will draw like this. I'll scribble those two guys out. You can replace it with a third line in green. And if I imagine that these things were written with the symbols before, it would just be exactly like, well, I would say, yeah, I take A and I tensor it together with B. I'm not going to be able to do the colors. And then I get that this is equal to C, possibly. But it's also possible, just as an aside, it's possible that you could also have, so there's a notion of plus that we just defined. Oh, it's a mess. Sorry. That's a mess.
It's a plus.
There's a notion of plus, and there could be another line D that's on top of it, or so on and so forth.
Yes.
Yeah. Okay, I'll clear that.
Right, which is also what we have in the OPE conventionally. That it's not that you just have two operators fusing into another. You have them fusing into some, usually an infinite sum of other operators anyway. So good. So very good. Okay, now we're going to see some pictures apparently. So okay, well here they just go over talking about the trivial object, that the trivial objects like the identity is good.
Yeah.
So now they have the three lines meeting at a point P, and okay. Interesting. Okay, well, this is like a slightly diagonal version of the picture you were drawing, it seems.
Yes.
So this is their A tensor B. Okay. Great. Okay. Now it comes to the other point that you made briefly when we were talking about the number of lines and so forth, is the notion of simplicity or semi-simplicity and finiteness. So for the categories being defined here, Justin's caveat from the very beginning comes into play, where they say that you have simple objects, and they're objects for which this morphism, going back to itself, is one-dimensional. In general, for any object, there's always a canonical identity morphism, which labels the identity operator on a line labeled by X. For a simple object, the existence of the identity morphism implies that there's a natural isomorphism to the complex numbers as an algebra. And so we assume that every object has a decomposition in terms of a finite sum. And so this okay, so n is non-negative, and A is simple. So every object X is semi-simple. This is sort of very similar to what you have in the story of the algebras. But basically the point is that there's a distinction between sort of simple lines and composite ones, and that generically lines are composite, but that the basis, as it were, is not itself infinite. That the basis is itself also finite. So that's the thing that they say here, we assume finiteness, that the number of isomorphism classes of simple objects is finite. And so that means that, as you said, U1 is not really covered by this, but like most discrete gauge groups are, or discrete symmetry groups are, all the discrete symmetry groups are.
Yeah. So what we're basically seeing is that the axioms of the fusion category are, roughly speaking, generalizing finite group zero form symmetries. And if you wanted to also include one form symmetries would correspond to topological point operators. Topological point operators would be Homs basically from the vacuum to the vacuum that aren't just like a boring. Right now we have that because one is simple, the Homs from the vacuum to the vacuum, there's only one of them, right? It's just like the invisible dot, if you will.
Yeah.
But if we had higher form symmetries, we'd have multiple dots, different dots that could live and be topological point operators. And if we had multiple topological point operators, that's basically saying that your theory is got multiple ground states, multiple vacua.
Yes.
And this topological
okay,
point
so
operators
we should kind of also go back for a second and say that, like, because higher codimension here in 2 dimensions makes what's higher codimension, then the line is going to be a point. So kind of going back to a point.
Yeah.
This is special to 2 dimensions. In higher dimensions, you're going to have a different picture.
Right. Yeah. I should mention. Yeah. So in particular, it's because it's a D-1 form symmetry. It's
right.
And it just so happens that D-1 is 1 in this case.
Yes.
Yeah. And you can actually include that sort of formalism, and then you get the magic of what are called multifusion categories. But in 2D, there's not a super lot of richness to such things. I mean, this is like an exercise for whoever cares.
Right.
But, yeah.
Yeah. Okay. Well, no, that's where it's good that you mentioned that. Now we'll get to something that we'll see an example of in some of what you told me to actually read, which is in the associativity structure. So the data in a symmetry category C includes certain isomorphisms implementing associativity of objects. So there's alpha ABC, which is in Hom A tensor B tensor C, comma A tensor B tensor C. Okay, and in pictures, this is what alpha is doing.
Yep.
And it is okay. It's called the associator. Is that right? Is that the parlance of?
Yep.
Okay. Good. Now, what? Yeah. Why are we? Well, I mean, I guess it is important to talk about associativity, but it isn't that you have associativity here. It's that you have an object that associates the left-hand side of what we would normally call the associativity relation to the right-hand side.
Right.
That's what this is. It's not saying. I mean, normally, if you had associativity like you did in a group, you would say, "Aha! Well, this equals this."
Yes.
Which that's one statement. Whereas here, what you're saying is apply alpha. Okay, takes this to this, right?
Yes.
So
So
what happened to associativity, Justin?
So yeah. So we basically in a standard group products are associative, and so in that case, if we specialize, so what the associator is doing is it's basically saying it's taking this data of fusing A and B together and then C, and then relating it somehow to the answer you would get if you fused B and C together and then A. And the famous way that this is always drawn, maybe this picture will show up again later, but I'll just draw it.
Yeah, let's draw it.
So the famous way that this picture is always drawn is
Oh,
ABC.
mm-hmm.
Oops. Sorry, I'm always defacing your page here.
That's fine.
Okay. A, B, C, times, and then I'll write alpha. Okay, so I'll just go through what all this means very vaguely. So roughly speaking, here you see we have the lines A and B, and then they come together, they fuse into AB, or A tensor B, okay? And then C glums on and turns into A tensor B, tensor C. I'm going to drop the circles because they make smudges on the screen. And then conversely, in this picture, I have topological defect lines, and they fuse together. But in this case, it's B and C first. They fuse into BC, and then we get A tensor B tensor C up here. Okay, and the associator is basically saying that you don't actually have to have the answers that those spit out be identical on the nose. Physically, what's happening is if you imagined having a background connection that was captured by these defects, because we now know that like a background connection is sort of captured by these defects, then what this alpha is basically going to do for you is this alpha here. So these things will be the same up to this data that's captured by alpha. And what this alpha is going to do for you is it's basically going to tell you is if you present a connection in one way, and then you present the connection in a different way, you could possibly get a phase in the partition function. And that's related to what people would call an anomaly. So standard group like,
we should
I know.
Probably take a step back to explain the first statement about why the background connection is giving you the defect. Presumably what you mean is that background connection by itself is not that meaningful. The Wilson line associated with the background connection, that is more meaningful, and is that the defect you're referring to here?
I'm just saying, so if you have a connection on a manifold,
yes,
and in this case it would be like represented by a one form or something like that. Okay, if you have a connection on this manifold, then you can equivalently present it, and it's necessarily, well, okay, you have a connection on this manifold, then you can basically use Poincare duality to turn it into homology, and that just basically is a presentation of defect by
right. So well, I mean, what you mean is that you have a flat connection on a manifold. Then by Poincare duality, you mean there's a cycle that you integrated along, right? Yes. And that cycle, so the result of that integration is going to be the phase in the Wilson line, right? Because a flat connection is just A dot dl integrate over the line, and that's sort of what you put in the exponent, and the expectation value of that is going to be the Wilson line, but basically the data associated to it is still that line, and that's sort of. But what matters is not just the line; it's the the homology class of it, because you can shift A by A goes to A plus d alpha, and that's by Stokes' theorem. I'm going to tell you that there's going to be homology induced on this class of lines that you can integrate it along. Okay, good. So that's going to give some physical meaning to pictures like this.
Soon. Yes. Yeah.
Right?
Yeah. So I shouldn't have jumped ahead. I'm eager.
No, but that's good. It's good that we laid this out, because otherwise this looks like it wants to be physical. It's unclear where the physics is, and the fact that this associator has knowledge of the anomaly is also very interesting, and we'll come back to that.
Okay.
Okay, so then we have the dual structure, which is, if you have unitary operators in Hilbert space, you think of these as being created by some application of some unitary operator. Then it must be that there's a Hermitian conjugate, presumably.
Yep.
And
there's a whole bunch of compatibility axioms about it below. It's just blah. But I mean, it's just basically saying, okay, these lines that we've been drawing, maybe we should have been drawing them with little arrows, but you can draw a line that's like the same thing, but pointing in the backwards direction, or things like this. I mean, these are all axioms. Oh, look, you can see all these beautiful figures. I mean, these are all axioms that basically say that you can take these topological lines because for mathematicians, do they know that they're describing topological defect lines? No, but they're kind of building up a pictorial formalism. And this pictorial formalism is starting to tell them that they can bend these lines around and they can squish them, which if you knew that you were capturing the physics of topological line defects, then I mean, all of these axioms are again obvious axioms, right?
Yes. I think that's important to note that that's what these things are for, because otherwise these epsilons seem I don't know, difficult to motivate at the very least as to what the point is. But if you look here, it becomes somewhat clear that what you're trying to do is you want to be able to straighten out a bend. If you want to be able to straighten out a bend, stick in this epsilon so that you can associate this thing to 1, because you see there's a dual here. Arrows go in the opposite directions here. The arrows go in one direction. Similarly, you can do this the other way around. And then there's this circle epsilon, that's what the circle thing is meant for. And then you can straighten out bendy line,
Absolutely.
which is good. And you're right, this is, if you had a topological line operator, you would expect exactly all of this to hold. You would expect that. Yeah, okay. Good. And then there's the dimension counted by a loop. Okay, and there you see again circle epsilons, and epsilons play an important role. Okay. Let's just dive into this paragraph to see if we've understood everything there's to understand here. Okay, so in fact, it turns out that we can further argue that dim CCA equals dim CA equals dim A. Okay. To see this, place a small counterclockwise loop of line A around the North Pole on the sphere. There is no other insertion anywhere on the sphere. It evaluates to dim CCA times the sphere partition function. Now we can move the line such that it looks like a small clockwise loop around the South Pole on the sphere. This evaluates to dim CA times the sphere partition function equation, equating the two expressions we find in 3.19. Okay. This is a further constraint on C. Why is, okay, if the fusion category C satisfies this, then C is called a spherical fusion category in the literature. Why is that? Presumably this notion of spherical doesn't come from, well, does it come from the sphere partition function, or like what's going on here?
I mean, it's coming from the fact that, I mean, I don't know which way to motivate it from, but I mean, they're describing basically that the way that the lines, so I mean, mathematicians, I said mathematicians don't have the pictures. They didn't know that they were describing topological line defects, but I mean, I'm sure that did become obvious to them. And you can see basically from what this blob under 3.19 is just described is that, if you have this property, then you can relate dim of CCA to dim CA by this argument, precisely this argument that's been made. And that's an argument that basically, that topologically, I mean, it looks as if it was happening on a sphere. I mean, that's kind of like that's why it's called spherical fusion category. So in some sense, it is related to sphere partition function, but if for physicists, but I mean, really, it's just saying that these look like topological defect lines on a sphere.
On a sphere, right? So that means that, like, South Pole orientation reverses if you try to push this down to the North Pole, or the North Pole up, whatever.
Yeah.
You're gonna have, okay, cool. Okay, they mentioned the caveat that these aren't necessarily equal. Okay, there should be a morphism relating them similarly with the circles on the top. Okay. And these are probably other, okay. Here, I guess, is an important thing, which is unitary structure, which is what is making all this relevant to physics at the end of the day. Quantum field theories in particular is that, well, you want these to be, presumably all should have some Hilbert space realization. Like, all these things should be the result of some calculation where you have some operators acting on some Hilbert space, at least abstractly, and that you can. Okay, and so the unitary structure is telling us that there's some conjugation between M and the arrow going A to B to the arrow going from B to A. And that turns circle epsilons into epsilons, but the R and L get switched because of the Hermitian conjugation doing the flipping of the A and B when you apply it. And that has some pictorial representation. Okay, cool. Okay, so that's I guess one of the reasons there are more notions and so on. But like, okay, that's I guess enough of a textbook intro to the to the
Well,
notion of symmetry categories, but or to finite fusion categories. But we are
yep.
yet to see an example. And
Right.
so for the example, I shall go to your paper, Justin,
Oh.
the
Oh.
one you wrote with Ivan Pobrano and Jonas Nauser. Um, if that's the one you wanted me to talk about. If not,
Sure, sure. I mean, there's definitely examples in there, so
okay,
we'll
good.
see.
Well, I mean, I saw examples there that then connected to other examples. I mean, okay, I mean, we maybe don't have to jump into
Yeah, yeah,
the
yeah.
crux of
No,
the actual paper, but okay,
yeah, yeah.
let's just go to the intro sections.
Yep.
Because that's the level we're at right now. I'm at right now. Okay.
Yeah.
Okay. Great. Now
Yeah.
let's
So, yeah, I think if you go further down, there'll be a thing on that'll just give a concrete example of some fusion categories, and we can just do hand waving.
yeah,
Because
but I think there's some things to clarify already at this level.
okay,
Okay. So
ask away.
let's explain this picture, please.
Okay.
Is this a result of some S dualization on a torus?
Yeah, I get scared. Okay. Um, yes, these two pictures are okay. I get scared of the word when you say S dual because then it
Okay.
sounds like a strong weak duality, but I know exactly
No.
what you mean. You mean a
Yes.
modular S transformation?
Yes,
Yes, these
modular
two
S.
pictures are related by a modular S transformation. Um,
Okay, good.
yeah.
And okay, so here you're just laying out the mechanics of topological line defects in a 2D CFT, which is, I think, worth going through
Yeah, sure.
in some detail because again, these two are consequences of like all the sort of topological properties are, as we described before, consequences of void identities. It's just they're phrased slightly differently here, although I mean it's exactly what 2.1 is. It's just a statement of void identities. Um, so okay, so it commutes with all modes of the stress tensor, right? So that's a statement
Yep.
of void identities. And okay, the partition function you have here is basically the torus partition function traced over the Hilbert space with X. So this is like it's almost as if you're computing the one point function of X, but it's not really a point, it's really a line. So it's really trace X times what you would normally call the partition function.
Yeah,
Um,
and you taught me about partition functions when I was learning 2D CFT.
well,
So any
let's see
errors are
how.
also yeah, yes.
This
Um,
is yeah,
so
okay.
yeah, I mean, if you imagine you
That's
have your 2D
unfortunate. Okay.
CFT, 2D
Yeah.
CFT on a cylinder.
Okay.
um, you imagine you have your 2D and so it's quantized on a cylinder, right? So time is
Yes.
going up. Okay. Um, and then I've inserted X along what I call a space-like slice. I mean, this makes perfect
Yes.
sense. I've taken this line X and I've wrapped it around this horizontal slice, which is the picture on the left. And this is, I mean, you could think about it. This is like a twist line in the Euclidean time.
Yes.
So it's computing the partition function, but there's this operator X that whenever it sees a state that shows up in the trace, it's going to act on the Hilbert space appropriately, and it's going to apply the X action, which again could be like a G symmetry action to the state.
Yes, and you can see that just by trauterizing this. I mean, you basically can fill in some intermediate states, and you see that in the definition of the trace. That's exactly what you need X to do. Good. Now you can S as in modular dualize it. And there your notation is that it's trace over H sub X
Yeah.
of this partition function. Okay, and that's this picture.
Right. And I mean, what's important to note here is that, especially when we're being very picky, like we picked a kind of a quantization scheme. The quantization scheme is time
Yes.
runs up on the cylinder, is that lines that are space-like are operators on this undefected Hilbert space. And
Yes.
operators that are time-like, like on the right, Hilbert spaces are slices. And so now it's a different Hilbert space, right?
Yes.
It's a different Hilbert space. So then I'm just
Right.
taking a regular partition function and
But over.
but over the defect Hilbert space.
Good.
So
Good. Okay. Very good. Okay, let's take the example here where we have a line defect generating Z2 symmetry. So if you have a charged object under Z2 symmetry, then X flips its sign in front of it, right? That's
Yep.
basically what we usually imagine. And here's the picture that you were trying to verbalize when I was going over the word identity story.
Yes, sorry. Yeah.
No, of course, no. This is important. So this is a picture of what you would expect the defect line to do if it's the generator of Z2 symmetry. It basically counts the Z2 charge of phi. More generally, it's whatever the X charge is of phi. Okay, and now there's this picture where, imagine you're looking from the top of the cylinder. This is the insertion of X, and there's phi on the same time slice, and that's what's going to happen. But you can also have the situation, and I think you'll get to this eventually, but this also goes into your other caveat about lines and fusing and so on. So you can also have a situation where you're doing something like this. You have dot here.
It might be even easier to think about these pictures as being drawn in the plane, right?
Okay.
So you can imagine that
yeah.
that phi has been inserted all the way down at minus infinity in the cylinder, but that's going to become hard to imagine. So instead, just imagine you now down in the plane. The point operator is inserted at the origin. You wrap it with an X circle, and then because the X circle is topological, you can just squish it down as if it were never there, and then it acts by X phi. The picture on the right is it's related to a technical point in some sense. Well, it's not.
Yes.
I mean, in this sense, it's just I'm saying what happens. So the case on the left is somewhat of a special case of this more general thing on the right. It's I insert a point operator in the plane, and then I sweep the operator past it. What's going to happen? Well, it turns into X of phi. There's some normalization out front, but who cares? So if I imagine this was happening in a correlation function, let's say it'd be the correlation function of phi with X to the right is the correlation function up to some factor with X on the left, but now phi has been manipulated.
Yes.
Plus the correlation function of it's very possible that when I dragged it past, it sort of collected a topological tail. There's a very concrete example of that. I don't know if you want me to go into, but there's a very concrete example in the case of the Ising model where this would be super relevant.
Maybe we'll get to that. But okay. So but super quick. I mean, even in the Ising model, what you're doing is you're presumably going to talk about these Verlinde lines. So in any RCFT, there's defects associated with primaries, and basically what the action on a primary of these defects is given by the ratio of the modular S matrix divided by the 0J component acting on phi j. And now from this, it should be clear that the fusion involves the what do you call these again? The ends?
The fusion coefficients.
The fusion coefficients, right? Yeah, I guess. Yeah. So just as you would have for actual for actual partition functions, here you have just for the two lines. I mean, it does translate because you put these in expectation values, and you're talking about like the chiral halves of partition functions, and then it's the same sort of formula that you would see in
absolutely
at the level of partition functions.
It should just be stressed that all of this fusion category formalism that was being discussed previously works for topological defects in any quantum field theory, basically.
Right.
Without too many caveats. But in this particular case of conformal field theory, you can really just, make all of this super explicit, right?
Right.
And 2D rational conformal field theories are enriched with exceptional sort of exceptional examples and very easy to find examples, let's say, of interesting fusion category symmetries, which are not just group-like.
Yes. No, that's it's good that we have this concrete handle. We'll be able to dig deeper thanks to it. Okay, so here though you say this is the caveat that you drew up there. So when you have this defect line sweeping past a local operator, it's not just that you're going to have a local operator, but then you're going to have a local operator plus a defect operator phi prime that lies on the end of a topological tail joined to X, right? So that's this. And you do mention that there's an example that you'll see. Okay, so let's, I guess, get to concrete examples.
Okay.
Okay, that's
So
yeah. So that's the
other
section.
background. Yeah. This is
Okay,
just other
so
background.
here, yeah, it's just other background. So you're denoting the abelian symmetry A. You have you call the CFT T on M, and so here okay. So there's the A connection.
Yes.
Alpha,
Yeah,
which is
yeah,
flat.
yeah. A is the group, and alpha is its connection, is its flat
Yes.
connection.
Okay.
Yeah, sorry about that, but I have to write
That's
A to
fine.
stress that it's abelian. So
Okay. Yeah. Okay.
yeah.
Good.
Yeah.
Okay. And then alpha labels holonomies around the different cycles of M. And this just is going back to what we described before.
Absolutely.
There's the pairing between H1 and basically integration cycles associated that should integrate alpha along. And because this is an element of H1, you only care about the homology class in which those cycles are, essentially. Okay. Now, that in turn implies that a background A connection, not to be confused with alpha being a background connection, but it also does, but just okay, is a network of topological A defect lines meeting at trivalent junctions. Why trivalent?
You can have n-valent, but everything just reduces to being trivalent junctions. You can basically turn any statement about n-valent junctions into trivalent junctions. So without loss of generality, I'm happy to just talk about trivalent junctions.
Okay, basically because it's this associator business, presumably that you're going to be able to.
Yeah, it's related to that. But I mean, all this can be said in a less heady way, because this is like all a bunch of blah. I mean, let's say it in the most lowbrow way we possibly can, right? What we want to get to is we want to get to the notion of orbifold, and that's just a fancy way of saying to gauge a discrete symmetry. Okay.
Yes.
So when you gauge any symmetry, what do? You take your theory, you write down the partition function, right? And then you have the action, and the action is like S, and then you also have S of A, right? There's some background field. And then when you do the Feynman path integral, you write, you have your D of phi, that's like, making all of your fields, like your phi fields quantum. And then you also add in D of A, which says also sum over all the background connections. In our case, like if we imagined we were on a torus, there's not very many background connections. It's just like a background connection with, and we know now that background connections are represented by topological defect lines. So there's basically a background connection for each way to put some lines on the torus. So label all the different holonomy, like A holonomies on the torus. So I mean, if we imagine is that 2 case, there's only like 4 different partition functions, and we sum them up, and that's called the gauge theory.
Perfect.
So that was
good. Yeah. Well, I mean,
but
yeah, I guess the other thing to note is that, okay, normally when you say you have a background gauge field, you assume that, say we're doing you're doing like just theory of some free fermions, and then you add a background gauge field, and well, there's going to be a coupling to the gauge field through the current. But now the gauge field has its private dynamics, which is given by the Yang-Mills action. Now situation's a lot simpler when you're in 2 dimensions.
And also when the gauge group is discrete, because now it's flat. Yeah.
Yes,
absolutely.
So I mean, technically what you're doing is technically you could write this presumably as, you do some sort of BF. It's like you're sticking in some kind of BF theory with some discrete gauge group, and then you could probably work out the very same formula that you get in the end, which we will show from that perspective. But the point is that the actual action isn't doing all that much at this point. I mean, most of it isn't doing all that much. There will be a piece that will, and that I think is going to be important in some of the discussion to follow. But for the most part, you could, in principle, get away with just doing the sum over A's and so alphas in some sense. Good. Okay.
I mean,
yeah.
The 2.8 is basically the most obnoxious way of writing the statement.
Let's get it. Let's get to it.
Yeah.
Orbifold theory. T mod A. So this is theory mod the gauged by abelian group A. That's what you mean by this.
Absolutely.
Okay. So as is familiar from the path integral, gauging symmetries, making the background connection dynamical. So the orbifold is obtained by summing over the twisted partition functions. Okay. Moreover, when we orbifold, there's an emergent dual symmetry, which is given by the Pontryagin dual A hat of A, which comes from the action of Wilson lines for the A gauge fields. This new dual symmetry can be coupled to a background flat connection beta. Okay, so you basically have a. Okay, so there's this is like your BFing this other thing in a weird way. It's not quite BF; it's just more like BA, but then this is a flat gauge field. You're not really doing the integration. Everything's discrete, so it's
this also sometimes goes by the name quantum symmetry from stuff in string theory. But I mean, it basically just says if you have this orbifold, so you start with an arbitrary theory T, it has abelian asymmetry.
Yes,
you can construct the orbifold theory T mod A. That's just summing over all the background connections. Just so happens that the theory T mod A has itself a symmetry, has also a global symmetry, and it happens to be an A hat symmetry where A is the Pontryagin dual. A hat is the Pontryagin dual of A. And this formula 2.8 is just a way to take the partition function of the orbifold theory on the left, the gauge theory on the left, and to take its partition function in the presence of the background connection beta and write it as a sum over the connections in the ungauged theory on the right.
Right.
And if you imagine that the trivial example is beta goes to 0. So if you just wrote beta equals to 0 on the left-hand side of that case, what do you get? You get 1 over the size of A, 1 over the size of the gauge group, and then a sum over all connections. And then there's no phase out front. And then it's a sum over all the twisted partition functions. So that's just exactly what we were saying before.
Yep. And yeah, I guess the important thing is that even if you did this in the path integral language, even though the actual action doesn't do much in 1+1 dimensions, there's still the volume of the gauge group that you need to mod out by, because this is the gauge theory. So that's still going to be an important factor. We'll come back to the this notion of Pontryagin dual, but for now let's proceed because there's more.
I'm sorry that
this is not but this is not the most general possible way to orbifold by a symmetry. In particular, one can include extra U1 weights epsilon of alpha in front of the twisted partition function and still obtain a gauge invariant partition function, which in the CFT language is known as a choice of the discrete torsion. And such a U1 phase is classified by a group cohomology class, which is H2 of A valued in U1. So this is so you mean H2 of A valued in U1, not the relative relative cohomology between A and U1, right?
Right.
That's
I mean the group cohomology of the group A in the coefficients U1
with coefficients in U1. Okay, good.
Absolutely.
Not okay, cool. Because
yeah.
Notation is it gets a bit confusing, but no, so why is this in H2? Where did this come from? What's going on?
Ooh, okay. Yeah, that's a heck of a story. So there's 2 different ways to think about this. There's a few different there's maybe 2.5 ways to think about this. Okay. One way that you could think about this phase that's out front is you could roughly think about it as being like discrete theta term kind of dealio. Something like this. Okay?
Something like that. Perfect.
Yeah. The way that you would say it in an old school way that would be more familiar to CFT is
to me
this notion of discrete torsion. So by discrete torsion, what I mean is you're doing some sort of sum look, I mean, from a physics principle, you know, and you know, there's nothing magical about why you would weight the sectors like all with ones. I mean, you know, or something like
Sure.
that, like with no phase. I mean, why not just put a phase in, right? Like,
Yeah.
who's
Okay.
stopping you? Anything that's allowed, you should be allowed to do, right?
Okay.
So, and it's very possible that you can weight these things with different phases, and you could say that's what the discrete torsion is. There's this. And then it just so happens that when you look at the sort of consistency conditions for like modular invariance in the case on the torus or something like that, that those are classified by things in H2. Okay. Perhaps the most famous example of this sort of notion of discrete torsion is actually in the case where the gauge group is like a Z2, but it's a Z2 for fermion parity symmetry.
Mm.
And then what you're doing is the most famous example of this is actually in GSO projection. So in
Okay.
GSO projection, you're writing down a fermionic quantum field theory. Okay.
Yes.
But then when you do the GSO projection, what you're actually doing is you're summing over spin structures. And
Yes.
there are two different ways to sum over spin structures if you write down like the type two, or you write down the superstring action, right?
Mm-hmm.
And you can sum over spin structures with one choice of this phase, or you can write it
Mm-hmm.
down with the other choice. And that's what leads you to type 2A or type 2B. Okay.
Okay.
The very modern hot way of talking about these things is you talk about them as SPT phases.
Okay.
Oh,
Let's get
yes,
to that. Yes. Let's
right.
get to that. So anomalies of 2D theories manifest as phase ambiguities in the coupling of the theory T to a background connection, which in turn are encoded in a cohomology class mu3, which is in H3, of A valued in U1. When a theory is anomalous, we don't just need to know that the cohomology class is trivial, but must pick a trivialization in H2 that consistently resolves all phase ambiguities. Alternatively, we may view the phase as the partition function of a 2D symmetry protected topological phase. Okay. Then orbit folding with discrete torsion is equivalent to taking a non-anomalous theory T with phase ambiguities already resolved, and then stacking with such a 2D symmetry protected topological phase before orbit folding. Okay. Okay, this is a lot.
Yeah, that was yeah.
So, no, I get. Okay, this does clarify a little bit more why this needs to be in H2, because you have the anomalies themselves being in H3, and then here you're saying that you must pick some trivialization
Yeah.
that resolves all phase ambiguities. But yeah, I mean, I do wonder if maybe the only way to get a clearer picture of this is to go further into this example,
Yeah, it's
or
possible.
not. It's possible. Okay.
I mean, yeah, I mean, from a mathematical standpoint, you know, if I just say, you know, you have this cohomology class and it's zero, I mean, that's not enough to resolve. I mean, at the end of the day, you're going to have to do calculations. I mean, this is just what I'm saying about trivializing phases. You're going to come to points where you're going to have to decide, like, okay, I can't just know that the cohomology class is zero. I have to actually know like how exactly it trivializes, and then, you
Yes.
know, roughly speaking, you're picking that trivialization. Alternatively, and I think this is much more physical, is there's this very hot topic of symmetry protected topological phases, which are gap phases, which are indistinguishable from the trivial phase. So that's just like the nothing phase. If there's no symmetry, a very lowbrow way of saying it is these are theories whose partition function, like what a partition function eats in a manifold and it eats in a
Yes.
background connection, right? The trivial theory is always got partition function 1 when normalized properly. SPT phases are theories that have partition function 1 when there's no background connection, but when you turn on a background connection, their partition function is just a phase. And so you can think about it. You can think about it as you have some theory called T, and then you take a theory which is basically trivial, except that it responds to being in the presence of a background connection, and that's called SPT phase. And then you just layer it over top of your old theory, and then you gauge. And then by doing that, that's like what setting the discrete torsion is like doing.
I see. No, that's very interesting. You know, it might be a little out of left field, but there are people in the matrix quantum mechanics literature that are thinking about similar ideas. I mean, there's a whole back and forth in that world about the point of gauging. So
Mhm.
for the purpose of a lot of calculations, like it's a paper by Maldacen and Millikan or somebody else, where they showed that like actually, if you look at the BFSS holography, you don't really need to gauge to see that only an order n number of operators play an energetically I play a dominant role at low energies. It's as if of the n squared operators you could in general have, the ones beyond the single traces, they're just energetically disfavored. And this sort of led people down different rabbit holes, and they might have discovered some very analogous gauging procedures just
Mhm.
without knowing the rest of the words. But it would be curious to kind of figure out whether what they're doing is in any way analogous to this, and it would be one dimension down. It'd be probably much more trivial, more interesting. I don't know. So no, but that's good. It's actually interesting to appreciate that this thing is itself like either the IS in the presence of some background gauge field alpha for this SPT phase, which is okay. No,
Yep.
that's good. I think that definitely helps.
Yep.
Cool. So here you
Uh,
go.
this is just explaining the partition function details we actually went over earlier and the origin of that quantum symmetry that I alluded to.
Okay, so here it's Z2, right? Yeah,
Yeah.
A is Z2.
Yep.
Okay. So now you're saying that sorry. The untwisted orbifold partition function on the torus is the following, where you have in the sum G and H in Z2, which is alternatively written as the sum G in Z2 of HG times this. So these are like presumably your two pictures that you had before. And this term in the round bracket projects us onto the states, which are invariant under the Z2 symmetry when we trace over HG. Makes
Yep.
sense. Okay, this shows that the operators that contribute to the untwisted orbifold partition function are those in both the untwisted and twisted Hilbert spaces, H plus and H minus. So H plus untwisted, H minus twisted. Okay, and those are invariant under the Z2, but to only those which are invariant under the Z2 action.
And that's just saying that you're taking the theory, you're taking it in the presence of the background connection, not in the presence of the background connection, and then you're taking all the states which are just gauge invariant.
Right, exactly. So that's what you're writing here, that you have these odd and even subsectors.
Yeah.
Then the untwisted orbifold Hilbert space just contains the even gauge invariant operators, while the twisted orbifold Hilbert space contains just odd operators. Aha.
Mhm.
Okay. Let me see if I get why that is. Twisted orbifold even operators. Okay, I agree that those are the gauge invariant ones. Yes, because okay, you're saying that you've in your twisting procedure, you're doing this, right? Okay, so you're sort of doing sort of a trace over the yeah, you're doing the trace over the even bits. And okay, then you also have this Pointryagin dual here, the emergent Z2 symmetry that appears in the definition of this new twisted orbifold Hilbert space. So now so this is kind of I guess your simplest case. This probably is from the next section. So okay,
Yeah,
so
that picture,
so that picture doesn't apply to this setup. Um, okay. Yes. Do I see this? So okay, let's go down a little bit more slowly. So here you want to consider the orbifold partition function untwisted. So here you just want to look at the sum. Okay, so you're looking at the Z2 gauging of this partition function. And so that is nothing but the thing here. Okay, let's see if I understand that. Yeah, I agree. Okay. Yeah, I'm just absorbing this a little bit slowly,
Yep.
but it is getting there.
It's okay.
Okay. Nice. Okay. So that's very simple, but okay, we haven't gotten to this part that you promised that we'll see an example of. For that, we need the Ising CFT.
Yeah. So
Okay, cool.
yeah.
So here,
So
what we're doing is,
oh yeah.
go.
Okay. All right, I was just going to say, like, yeah, I mean, to walk you through the example, the using CFT is the most famous CFT. It has three primaries: one, the identity, the energy operator epsilon, and the spin operator sigma. And I also list their conformal weights. It's also well known what their fusion rules are, right? You just go into Ginsburg and you look them up, and they fuse like this. So if you bring two sigmas together, it turns into ones and epsilons and their descendants. And then similarly for sigma and epsilon fuse to one. Okay, fine. Also, this Ising CFT turns out it has precisely three simple topological defect lines. So simple in the sense of like most fundamental.
Yeah, well, okay.
Yeah, they're labeled by primaries, and those are
Right.
also the Verlinde lines because of
Yes.
this particular case we're tracking. It's very obvious how the identity acts on operators, local operators. X epsilon is the Z2
Is
symmetry line.
like the one we just went over
Absolutely.
in the previous example. Yeah.
Yep. And then there's a third line called X sigma, and it acts as it.
Okay, that's what this is for. Okay.
Right. So you can see it's actually, if we start with the picture on the right, it's when it swaps past an energy insertion, the energy insertion gets a sign. Yeah. But on the left, when you sweep it past sigma, it turns into mu, right? So mu is and then this mu operator is on the end of this X epsilon line. So it's on the end of a Z2 line. You probably know mu's. I mean, if you've read Ginsburg, right? Because mu is if the sigmas are called order operators, then mu is a disorder operator.
The disorder field, right?
And it has to sit on the end of the Z2 twist line.
Right, because the disorder operator is a line with the tail. Well, it's the tail of a local operator. So it's a local operator with the tail. So it's almost a non-local thing. I mean, it is essentially non-local, but it comes with ends.
Right. So from that framing, the sigma looks as if like when you sweep that defect line past, it turns the sigmas into mu's. And then you can use this to basically turn collections of correlation functions of sigmas into correlation functions of mu's. And this is how you can actually prove Kramers-Wanier duality. Because what you could do to prove Kramers-Wanier duality is you could assume you are at the Ising CFT at the critical point, right? And then you have a correlation function of sigmas. You pop a clump of the defect of the
sigma defects.
Yeah, the sigma defect into existence. You sweep it past everything. It turns it into a correlation function of mu's. Okay. And then that's at the CFT point. Okay.
Yes.
But then you also imagine you insert in a little bit of epsilon operator into it, or an exponential of epsilon operator, right? And that's going to basically flow you to different temperatures. And so in one, you can see that it's like e to the blah 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 epsilon, but it's got a positive sign. And then when you sweep it past, it flips the sign on the epsilon, and so it will run you to negative temperatures.
Right. So you're gonna have or you mean the inverse temperature? So you have like high low temperature duality, which is sort of the original statement of the Kramers-Wanier duality, that you have the spin fields. And that's also why you need these things these mu's in this. Okay, I mean, like in the dual frame, mu's are essentially local, but like in the original frame, what you have is the mu being like this thing with the tail, this local thing with the tail, and that's what this is, right? You have this X epsilon tail, and anything crossing the tail will flip because that's basically what the X epsilon is. It's a Z2 symmetry line. Yeah. So that's kind of like why anything here is going to flip as you move it across.
Yep. Yeah. It's beautiful story.
Very cool. Very cool. Okay, so that's
not original.
But that is also the what do you say? Use case of that general formula you had.
Absolutely.
Okay.
Oh my God, I just never stopped writing at the time, did I?
I know there's
I'm
more.
very sorry.
That's all good. Okay, so let's get to gauging.
Yeah. So So I mean, and yeah, just one other point is that this is what people call duality defects. So if you're on the archive right now, it's January 2023, you'll see many papers over the past few months, and maybe hopefully some in the future, about this sort of notion of duality defects. And the reason it's called a duality defect is because this historical case, that this example of a duality defect, the concrete example is in the Ising CFT, where it relates the Ising model at different temperatures. It's the Kramers-Vannier.
Yes.
It's a defect that, yeah, it's topological defect line that relates the Ising CFT in two dual frames. So, yep.
Awesome. Okay, so let's get to okay. So
Okay.
this was what you were talking about, these defect lines, and you said the duality defect lines. And
Oh
so
yeah,
it's
this
it's
is
not the non-simple topological defect line. That is,
yeah.
not by non-simple you mean the sum x1 x epsilon.
Yes.
Um okay, inserting a triangulating mesh of x of these produces T mod Z2. Makes
Right.
sense. So why not just these though?
So if you insert a triangulating mesh of those lines,
Okay.
you will basically produce the gauge theory, right?
I mean,
Um,
uh-huh. Well, no,
okay.
what I was asking was
Well,
here, right?
mhm.
Okay, so you're saying that I insert a triangulating mesh of these lines,
Yes.
and that produces this gauge theory, but I'm wondering why not just these?
Oh, because then you would only be capturing, like, if you imagine what x1 plus x epsilon is doing, it's
So,
basically when, yeah,
no,
when
sorry,
you're
go ahead.
sort of like inserting all these x1s plus epsilons, is they're basically capturing that. If you scroll up a little further, that sum over the partition function business, they're basically
Aha.
just kind of capturing that, right? And if you only inserted x epsilons, you would not be capturing, let's say, your orbifold would not be capturing all of the Hilbert space, very vaguely. I'm being very vague.
I see. Okay, well,
Yeah.
maybe it's possible to see from.
Another way to say it is, if we just think physically rather than in terms of lining up the math, is that when you're inserting this triangulating mesh, what you're really doing, if you imagine like it's a really fine triangulating mesh, right, like
Mhm.
small and everywhere, what you're basically doing is you're kind of like changing the vacuum to a vacuum that's, instead of being built out of one, the line just x1, it's being built out of
I
like a
see.
line like x1 plus epsilon. Okay.
Okay.
um yeah. And then
Okay.
the rest of the business about like the fact that the duality defect line squares the projector and stuff, that's all technical details that are relevant for this duality defects paper. So
Okay. Okay.
yeah.
But okay, no, I see what you're saying. Okay, so it's not just that if you take the, okay, so just because this is a Z2 line doesn't mean that's all you need to do this. You need the x1 plus
Mhm.
x epsilon to get, I mean, to get the full orbifold. Um okay.
Okay. Yeah,
So
that was a lot.
and there's more.
Oh no. Oh my gosh. I wrote way too much. Ugh.
Well,
But, you learn a cool thing, and then you want to tell the world about the cool thing you learned. When you should really just cite someone else who did it better.
okay, so I mean, this looks plausible to me. I mean, you don't have to go over the exact
Yeah.
derivation per se, but yeah, I mean, if you put everything in the right place, then I can imagine that these partition functions come out to be the sums of squares of these characters. Um, so then you say that, okay, so
That's calculating the defect partition
right,
functions. Yep.
okay, and now, okay, this thing appears again, but I think that goes into even further into the story. But I
Mhm.
think here it's already good that we sort of have a sense for like where, yeah, so for the, what's the saying, the hens coming home to roost.
Right.
Right, so we already kind of get a sense for like why you might need these non-group like notions of symmetry and how they're associated to defects. And well,
Yes.
here, I mean, really, it's not even that all these defects are symmetries per se, and they're certainly not invertible. Now, I guess we should just flash at least the abstract for the paper that you actually wanted to talk about, which we're just gonna have
Yeah,
to do next
sorry.
time, which is the orbifold groupoids. I don't know. I mean, I should be the one saying sorry because I just didn't have the background to absorb
It's okay.
this. I mean, it's
Yeah.
unclear whether I do now either, but
Oh,
there are
yikes.
there are okay. I mean, pictures that I can understand a little bit better now, right?
Yeah.
So here is the I guess okay, this is probably a similar phenomenon to what you were describing before with um, the gapped phases sitting on top of your 2D theory, um,
Uh,
where
it is related, but it is actually different.
okay, okay,
Yes.
okay.
Yeah. So
So
I could go into it, or if you need to
okay,
stop, we can.
let's. I mean, no, let's just briefly go into why. Okay,
Sure.
so what's going on here versus when you
Okay.
just had
I can
the.
explain to you what's going on here, or I can motivate why you'd want to look at this picture at
Okay,
all.
let's
So
let's
it's
go
up to
there.
you. Which would you prefer?
Let's
Yeah.
start with
Okay.
the motivation. Let's start with the motivation.
Okay. I can share my screen and I'll go
Yeah, share
fast.
your screen. Yeah, yeah. You can read
Yeah.
however much you want if you share your own screen. That's true.
Yeah, and it hopefully won't be as messy. Okay. Here we go. Okay. So let's see. Yeah. So basically, the idea of this paper is okay, we now know that higher form symmetries exist. We now know that non-invertible symmetries exist. We know that they're supported on topological codimension, blah, blah, blahs, right? We can
Yes.
fuse them and they merge and they have different charges under each other. Okay. Okay. Now we're going to be very vague. Maybe vague is not the right word. General. Okay. We're going to be very
Okay.
general. Okay. So given any quantum field theory, so like if I say given any QFT, I'll write a little bit fast. So I'm sorry if it's a little messy. So given any QFT, we can split it into sort of data into two different types, right? We can have local data,
Mm-hmm.
okay? And then there's also global data. Okay.
Okay.
So let's do some concrete examples. And as always, I'll just focus on 2D and we can use the language of CFT, but I should stress that the story that I'm going to describe to you works in arbitrary dimensions and doesn't have to talk about conformal field theories. Okay. So
Okay.
local data. Okay. Well, this is an example that's not in not necessarily in a conformal field theory because this object doesn't really make sense in a conformal field theory is the S matrix.
Okay.
So that's, describing scattering experiments. That's an example of local data. An example of global data might be something like the global structure of symmetry group, right? So
Mm-hmm.
the LHC will be able to tell you about the S matrix of the standard model, but it's highly unlikely to ever tell you about the whether or not the gauge group of the standard model is SE3 times SE2 times U1 or that mod Z2, mod Z3, mod Z6, or none of the above. Okay. A concrete example of local data is something like the operator product expansion. Okay. And then some global data is something like 't Hooft anomalies. And hopefully that's clear because the global structure of the symmetry group and 't Hooft anomalies are all kind of captured by this fusiony data that I nattered about. So, you can kind of see that those are on different footings. And then perhaps the most concrete example in the case of a 2D CFT is local data is captured in the chiral algebra,
Mm-hmm.
right? Which is roughly speaking, it's vertex operator algebra.
Mm-hmm.
Okay. The vertex operator algebra that describes it. And the global data would be something like the modular invariant, right? Because there are
Yeah.
some theories that have the same chiral algebra, left and right moving chiral algebra, but different modular invariants. Okay.
Fused differently. Yeah.
Yeah. So as a concrete example, if you imagine at C equals 4/5 in 2D, right? There are two bosonic unitary minimal models, right?
Okay.
There's the tetracritical Ising model,
Mm-hmm.
tetracritical, and then there's also the Potts model.
Mm-hmm.
Okay. And these are called the A type and the D type sometimes in the literature. Okay. And so their shtick is that these theories have the same OPE because they have the same chiral algebra. Okay. So that means they have the same 3-point functions, all that kind of stuff. But they correspond to different modular invariants. Different modular invariants, so different collections of global data. Okay.
Right.
So now this sort of begs the question. Okay. This begs the question, what are, and as an exercise that's not important, but one could then start to study notions of relative and absolute quantum field theories, but that's a whole sideshow for itself, relative versus absolute. Okay. But the idea is so let me phrase this in the form of a question. Okay. What are all topological manipulations of a QFT? Okay. Now, what do I mean by a topological manipulation? I mean, two theories, let's say, are related by a topological manipulation if they have the same local data. So have same local data, but different global data.
Okay.
Okay. But different global data. Okay. So in a concrete example, we would say that this tetracritical and this Potts model are related by a topological manipulation because they have the same local data but different global data. And in particular, maybe I shouldn't quiz you. The thing that relates them is a topological manipulation that relates them is gauging. Oops. Well, that's huge. Gauging the Z2 symmetry. Okay.
Okay.
Okay. So what are some examples of topological manipulations more generally, right? Well, it should be things that only affect the topological data. So if we think in 2D language, that includes gauging, aka orbifolding. Okay. So maybe I should just write them down. So there's orbifolding. I can stack with an SBT. Okay. And also this would include the GSO projection if you have a fermionic theory, or the Jordan-Wigner transformation if you have a bosonic theory with something that's Jordan-Wignerizable, so like a Z2 symmetry or something like that, right? But so basically everything turns out to just be captured in the notion of gauging or stacking with an SBT phase. Okay. And it's clear that this orbifolding doesn't affect the local dynamics because, I mean, it does talk to the original degrees of freedom of the theory, right? But the Z2 gauge fields themselves, if you're studying the Z2 case, but I guess I could be studying the finite group gauge fields themselves are necessarily flat, so they have no local dynamics. Okay. But this will change who is local. So it'll change who's a twist field, who's not. Okay. Stacking with an SBT phase, obviously, same thing, doesn't change local dynamics at all because what you're going to do is, you're basically taking a theory which is essentially trivial. It's like a topological quantum field theory, and you're just putting it on top of the other theory. Okay. And so it doesn't even talk to the original local degrees of freedom at all. That's what stacking is, right? Stacking means you don't change the local degrees of freedom at all, and you're definitely not adding any. So really all it's going to do is it's going to change how the theory reacts to a background or something like that. And then of course you could do this first and then orbifold, and then that produces a new theory. So it does kind of mix them up a little, but still adds no local degrees of freedom. So these are all the topological manipulations of a theory. Okay. But the point of the orbifold groupoid paper is the following. So I don't know. Maybe I don't know if I should spoil it or not, or maybe that's a teaser. But I can also spoil it.
Maybe a teaser so that we can, or I mean, your choice.
Sure.
So no, we can come back to this.
Yeah, maybe I shouldn't sign myself up for work. So okay. Jokes aside. Okay, so I'm going to give you the answer. So the answer is that all topological manipulations. All topological manipulations are controlled. Well, let's say, okay, suppose I have a quantum field theory, an arbitrary quantum field theory with G symmetry, okay? Like and G doesn't have to be abelian anymore, okay? Finite, somewhat discrete, but G symmetry, okay? All topological manipulations okay, are controlled by a G gauge theory
Mm-hmm.
in one dimension higher. Okay.
Dope. Okay.
Okay. So to make it concrete, right? So let me just, so there's some caveats here. So first things first, yeah, so G is discrete, but actually G can be more than just a group. G can be promoted all the way to a fusion category. Okay.
Mm-hmm.
And again, I told the story, you know, we kind of talked about 2D examples. And then so in this case, it would be a 3D G gauge theory, but you could talk about anything. Okay.
Okay.
Okay. So, and another thing I want to highlight is that the whole point of this formalism is that it talks about topological manipulations. So I'll just call them TMs for now. TMs in a theory independent way.
Okay.
Okay. Because at no point when you say, if you said to me, oh, what are all the topological manipulations of, and then you tell me your favorite theory, right?
Mm-hmm.
And no, I would have just said, like, stop, you know, you've told me too much. Okay. All you have to tell me is the symmetry group G
Mm-hmm.
or symmetry fusion category. And then I can tell you all different ways that you could take a theory with any local dynamics that has any choice of local dynamics that you have. And I can tell you all of the different ways that you can organize its global symmetry. So in some sense, yeah, so it relates to a topological field theory in one dimension higher.
Mm-hmm.
And yeah, then the theory of topological boundary conditions and everything becomes relevant. And the main picture that we kind of saw a preview of
Right.
is what it's going to do is it's going to take a 2D theory. I've drawn it here. Let me draw a picture of a 3D topological field theory. Okay.
Yes.
It's going to take your topological field theory T, or sorry, your quantum field theory T, your arbitrary
In
quantum
two
field theory T,
dimensions. Okay.
in 2 dimensions in this picture. And it's going to turn its local dynamics into
Mm-hmm.
a particular boundary condition for the
Mm-hmm.
3D theory. And then it's going to turn all of its topological information into a
Yes.
topological boundary condition on the other side. And so it
Mm-hmm.
blows it up into a picture like this. And then all the topological, so in some sense, we've quite literally separated the local questions from the topological questions, from the global questions, by using this picture.
Nice.
And then all the topological manipulations are just questions about this side of the picture here.
Mm-hmm.
And that's why it's theory independent, because basically, yeah, I literally separate the degrees of freedom and can only talk about this. And so
That's awesome.
that's the point of the picture.
This is yeah. Okay, that's very interesting. It's a bulk boundary relation which isn't even holographic per se. It's something else. But
Yeah.
it's really fascinating. Okay.
Yeah. Yeah.
Okay. Well, yeah. Let's get to that. No, this was awesome though. Thank you,
Yeah,
Justin.
so-
You've been you've been an ideal pioneer for this podcast to enter the maze of the GCS stuff.
the global categorical symmetries. Yeah. And I apologize to you and to anybody for how lengthy my writing apparently was on
No, that's fine.
on various
That's
topics.
totally fine. Well, I mean, I think that's all right. I don't think anyone's complaining about that. But it is it is very cool to have it broken down. And I think that at least for me, this was adequate motivation to actually go pick up a few more of those reviews at least, and sort of read them a little bit more thoroughly. Yeah, and I mean, you're definitely signed up now as a future guest.
Okay. Oh, all right.
I mean,
No,
in
I'm
many
happy
ways,
to do
this.
it.
Okay, well, I'm glad. I mean, in many ways, this is also overdue. But yeah, well, thank you again, Justin, and thank you all for listening so far. If you've gotten this far, definitely subscribe, leave a like, comment, share. This is Theoretically Podcasting, and I'll catch you all next week.